Okay, hi everyone. Welcome back. So this time a little quiz in the beginning. I hope it was fine for everyone. Not too difficult, right? I made the questions a little bit more difficult. The TA's questions were too easy. So, later there shouldn't be any complaint that the exam is too different than the quiz, right? So that's why. But anyway, I think it was still quite easy to solve. Hopefully, let's see. So next week on Tuesday, the TA will present the solutions. Yeah? And then after that, we have the next quiz. Or actually, Jui, maybe let's present the solutions on Thursday. Yeah, maybe that's better. Yeah. Okay. And because otherwise we have like a too long period in the beginning of Tuesday. Okay, yeah, you can go. See you. Okay, and maybe some of you are not familiar with it, but the quiz or exam in university, we need to take this serious, right? For fairness, like everyone should be treated in the same way. Someone who studies hard and who knows how to solve problems should get a better grade, right? So please, no cheating. Yeah, we will be very rigorous with that. Everyone sits next to each person, so just a single look on the paper already help him to understand what he's doing, right? So we have to be like really strict with this. So also no smartphone usage, obviously. Next time, just make sure that on the desk you have only the ball pen and the calculator. That's all you need. Yeah. And if we see anyone like using some other tools, looking at the partner, then we will just give 0 points immediately. And if this happens like 2 or 3 times, then this may even lead to failure of the lecture. Okay? So please just make sure to not use such kind of ways. And in the exam, this will be actually even more serious, because in the exam, if it happens in one quiz, this might not harm you that much for the grade, but if it happens in the exam, this might be a really big problem, right? So just make sure you do this regularly in a fair way just think about your other students and your friends, right? It should be fair for everyone. Okay, so let's come to the lecture. So what we discussed last time was kind of the picture of the atom, right? So actually, let me come to the figure here at the end. So we found out a couple, we looked into all these different experiments, right? Showing that the atom consists of a nucleus, which is made up of protons and neutrons. And this thing, nucleus, is really, really small, right? And then there are somehow these electrons, which are extremely tiny, and they are somehow flying around here, right, around this nucleus. These protons are positively charged, the electrons are negatively charged. And the electrons are somehow on some very specific distances from the nucleus. And that's kind of the picture how we ended up, where we ended up. And we looked a little bit into like how we can classify the different elements. We introduced these, the number in the periodic table, which tells us about the number of protons and electrons for a neutral element. And from the mass, I mean the number is actually the particle number in the nucleus. We can know how many neutrons there are, just the difference of the with the number that the element has. We can also try to charge up these elements by adding or removing electrons. And we learned that we can also add or remove neutrons to make isotopes. Right? So add or remove electrons, and we have charged atoms, and or remove neutrons, and we have isotopes. So starting from this periodic table of the elements, we can do these things. And what we also learned is that this doesn't usually affect the chemistry, right? Does not affect chemistry. At least not very much, right? It might affect a little bit, but not that very much. That's why we usually don't put a separate isotope in the periodic table. We just group them by their number of protons and electrons. Okay. That's also what we did. Then I think we ended up with this figure summarizing all that process. And I told you in the very end that there's a bit more to it, like there's quantum mechanics, which tells us that the electrons and the neutrons and protons, they're actually also waves, they're not only particles, which makes the story a bit more complicated. And it's hard to think of an atom like, in our perspective, of particles that we're used to. But there's a theory that we can use to develop this. We can basically marry the concepts of waves and particles together, and that is what quantum mechanics eventually is. And that is also the reason eventually why the electrons can be only at certain distances from the nucleus. I will not go too much in detail with this anymore. Any questions to the last lecture? No? Okay, then let's continue. So now we want to look a little bit into the formation of chemical bonds. So atoms can, in fact, come together and they can start sharing electrons. Yeah. So let's say there's a second nucleus coming in here, and it also has an electron here. And then they can actually form, they can share these electrons together. So basically this electron can sometimes be here, this electron can sometimes be here. So they start to profit from each other. Like one atom becomes more stable because he has partially another electron there. And maybe the other element might be more stable as well because he has partially another electron there. So apparently the atoms can benefit from sharing electrons. That can make the whole thing more stable than it was before. It's usually what we call a covalent bond. And once you have these covalent bonds, then you can form these molecules from atoms, which are collections of atoms connected by covalent bonds. And if you want to write down the formula of that kind of molecule, which is connected by covalent bonds, you have different ways to do this. There's a chemical formula, a structural formula, space filling, ball and stick, many different more. We will look into this. So what is the chemical formula? The chemical formula uses the symbols of the elements to indicate which elements, which atom type is there in the molecule and how many of them you have. And the subscripts indicate the number. So for example, CO2, you have 2 oxygen atoms, 1 carbon atom in that molecule. That doesn't tell you anything about how these are connected with each other, right? With covalent bonds. We don't know how they are connected. We just know that there's 1 carbon and 2 oxygen atoms per molecule. And we know that all these experiments I showed you last time, they help us to understand the ratio of these elements, right? All these mass measurements, gas measurements. But then there's also a structural formula. The structural formula depicts the individual bonds in the molecule. And they might also be used to indicate the shape. So, for example, for the methane molecule, which is CH4, you have a carbon atom in the center, and it's connected to 4 hydrogen atoms. And you can actually use these dotted lines or dashed lines to indicate that the hydrogens are lying like behind the plane of this projector. And this one is kind of lying in front of them, right? So if you just imagine that a little bit, this becomes like a pyramid, right? Pyramid with 2 lying in the back and 1 lying in the front. And then this one is exactly in this paper plane. The space filling model is a little bit more fancy, like 3D illustration of this. Maybe this is a bit more easy to see from this. There's also ball and stick models. Like all of these can be used to better understand the arrangement of these atoms, right? The structural formula is probably the most important because you can actually include this kind of 3-dimensional structure via these drawing the lines in the more bold or dashed way. And at the same time, you can actually indicate the bonding quite well, right? And you can draw this one on the paper. This one you cannot easily draw, right? So this is something which we need to learn, like how to draw these structural formulas. And then, now I discussed with you the covalent bonding in molecules where we connect one atom with another atom and we draw this structural formula. But in some situations, the atom doesn't want to share the electron. Sometimes one of the atoms wants to get both of them, and the other atom actually wants to get rid of the electron. So it can be also favorable that there are 2 atoms here. This one has an electron here, and this one has an electron. And this electron completely moves to the other side, so that essentially after this, you have 2 electrons in one of them and 1 electron in the other. And let's say this was 1 plus before. Now this one becomes net negative, right? And this one becomes net positive, right? So in this kind of situation, we call this an ionic bond. And what you formed is ions. It's a cation here and an anion here. A cation is something which is net positively charged, an anion which is net negatively charged. Yeah. So the anion is formed by accepting more electrons, cation by giving electrons. So we need to better understand in what situation do the elements like to share the electrons, in what situation do they like to transfer the electrons to form ions. So this is something we need to learn in the next lectures more. And covalent bonding and ionic bonding, so they have quite different character, as you can imagine, right? In the covalent bond, the electrons are basically shared between them. So you form a different shape of that electron distribution. While in this case, the electrons are basically in this atomic shape of that element here, right? They go into these circuits or regions of that atom, right? And eventually you simply have something like an electrostatic attraction between plus and minus. Okay, so here are some examples where ions can form. So just imagine that you have a sodium. Okay, sodium, you can see it's here in the first column of the periodic table, right? So apparently, sodium is an element which likes to lose an electron, yeah, which makes it more stable. So sodium could form a sodium plus an electron. And you may see this is already like a chemical equation. Like this is a chemical reaction, actually. This is an example for a chemical reaction. The mass is balanced on both sides. We have same number of electrons, same number of protons, same number of neutrons on both sides. It's a chemical equation, right? Okay, at the same time, we need an element which really likes to get an electron. and that is in this case chloride. You can see chlorine is exactly on the opposite side in almost the last row, not the last, but the before the last column. So apparently chloride likes to get an electron. And it's actually not by incidence that this is the first row and the second last row. This is exactly how the periodic table was constructed. By people realizing that kind of optimal match. So sodium and chloride, they form an optimal match. Sodium likes to get rid of the electron, chlorine likes to get it. So they will exactly do something like this. They will do an ionic bond. So if you put a sodium and a chloride together, you will form these ions automatically. Yeah? This is just sodium chloride. This is what you use probably every day for cooking, right? And you dissolve it in the water, and that's it. Okay. But ions don't need to be just a single atom. You can also have many atoms together. You can have molecular ions. Okay. So you have, these are also called polyatomic ions. Example here is NH4 plus. NH4 plus. This is called the ammonium cation. It's a nitrogen atom connected to 4 hydrogen atoms. Okay, so this is a polyatomic ion. It is nitrogen with 4 hydrogen. Apparently, this is plus. Yeah, has a net positive charge. You can again remember this means this hydrogen points to the back. This is to the front. So you have a pyramid, right? Nitrogen with 3 hydrogen pyramid. These are lying in the plane of the body, right? And at the same time, you can also have negative ions like a nitrate, right? So again, you can have like a nitrate ion, Ni. So this would be an Ni. This would be a cation. So it doesn't need to be atomic. It can be also molecular. Okay. So to be honest, I don't really understand this question at this point because the book doesn't explain when something is losing electrons and when something is gaining electrons. So I would skip this at this point. We will talk about this later in more detail about the rules when something is losing and when something is adding electrons. Let's do this one, however. So how can we form an ion? Okay, so A, by either adding or subtracting protons from the atom. B, by either adding or subtracting electrons from the atom. C, by either adding or subtracting neutrons from the atom. D, all of this is true. E, 2 of these are true. Okay. So what happens if we add or subtract protons from an atom? Is this a way you can form ions? No. This would form a completely different element, right, if you do this. And this is not a chemical reaction. So a chemical reaction is about changing the way that these atoms are arranged by changing the electrons, right? Chemistry is, usually people say, the physicists would say, chemistry is the physics of electrons. Right? Well, you could consider this as kind of downgrading chemistry to be just a part of physics. It's kind of true. I mean, chemistry we do the physics of electrons, right? And you could also say biology is the chemistry of life. Or you could go further and you could say medicine is the biology of life or something like that. So you could go down the grade and then eventually physics will be everything, right? But in the end, this is kind of true. I mean, when we do science with electrons, that's what we do with chemistry. We don't touch the protons usually. We don't change the elements, right? Already said. Now I think so. B is right. By adding and subtracting electrons, we form ions, right? Okay, but that's for an atomic ion. We can also have like reactions. So that's why this question is not complete. Like we should actually say how is it atomic ion formed? Because for molecular ions like this, we can also form them. So for example, let's say you have ammonium and you add a proton and you form an ammonia. Okay, so here you have NH3 and you add a proton to this, or this is also called a proton. This is actually a hydrogen cation, and then you form this ammonia cation. So that is why this question is actually not entirely accurate, right? Because you can actually add protons and you can form cations, right? But it's not you are adding it to the core of another element. You're just changing the arrangement of these atoms, right? You're just adding another bond here, right? So that's why I don't particularly like the question. It's a bit difficult to understand, a bit misunderstanding. So you can actually add protons and charged particles, and you can make larger charged particles. So you can form ions, right? Molecular ions. Okay. An element's most stable ion forms an ionic compound with, let's see, is this possible to solve at this point? Okay, so let me explain you one thing then for this. So if we look at the periodic table, I already told you that the first column of elements, like sodium, but not only sodium, actually also potassium, lithium, even hydrogen, they like to lose an electron. Yeah, that makes them kind of stable. So there's a reason for that. I think we will talk about that later in detail. It has to do something with the filling of the shells of electrons. But anyway, for now, just consider that these like to lose one electron. The second column, beryllium, magnesium, calcium, they like to lose 2 electrons, right? So it's pretty obvious that we would like to have an electron number which matches the last column, right? Just imagine you would take sodium and you would remove 1 electron, right? Then you would exactly have the same electron number as neon, right? Or if you would do the same thing with potassium, you lose 1 electron, you get argon, right? They are not exactly the same because you have a different number of protons and neutrons, right? But the electron number is the same, right? Electron number. Okay, so we could think about that the elements like to become noble gases. The last column is usually called the noble gases. Okay, so elements have a tendency to become noble. And now we also understand why the halogens, which are chloride, fluoride, they like to get an electron. Why? because they become noble if they get an electron, right? So noble gases are very stable, and every element prefers to be noble. Yeah, that's the very simple rule. Actually, we can introduce for now. Okay. So based on this, we can maybe look into this question. An element's most stable ion forms an ionic compound with chlorine and has the formula XCl2. If the ion has 36 electrons, what is the element from which the ion comes? Okay. So think about this for a moment. Okay, so who thinks it's A, proton, B, selenium, strontium, rubidium, and none of this? Almost everything is in there. So what is the charge of the chlorine here in this element? It's an ionic compound. So how many electrons does the chlorine want to get? One. Just one. Then it becomes argon-like, right? So the chloride should be -1, right? Cl-, okay? But we have 2 of that, right? So what should be the charge of the X cation so that the whole thing is neutral? Who thinks is 1, 2, 3? Okay, why do you think it's 3? I mean, we have 2 chloride, right? Cl-, Cl-. -1 plus -1 is -2, right? Total should be 0. So what should be the charge here? 2 plus. Makes sense? 2 minus 2 is 0, right? The whole thing should be neutral. Neutral means charge is 0. Yeah. I hope that makes sense to everyone. Okay, with that, let's think about this one more time. So, what is the element from which this ion comes? So the ion has 36 electrons. How many electrons did the ion have before? Sorry? 38. 38. So it lost 2 electrons, right, to become 2 plus. So now you only have to look at the periodic table. And what is the number 38? Strontium, right? So C is the correct answer. Okay. So you already see the periodic table is really useful for a chemist. It's kind of the toolkit we should always have in our pocket when we do experiments, because we can easily predict many things. What I just showed you was just one example, but when we look more into quantum chemistry, you can see there's much more information in how these elements are ordered. There's a very systematic way. And originally it was not thought like that. I mean, the periodic table was made before quantum mechanics, right? But the reason for that disordering is also matching quantum mechanics is that people did this ordering based on their properties, right? So people realized that all these elements, lithium, sodium, potassium, rubidium, they show very similar chemical reactions. Their chemical properties are very similar. So they ordered them by mass along that column, right? And in principle, all these elements are ordered by mass, right? You can see always we add one more proton to this. But at the same time, you order them also along the column by their chemical characteristics. So that's the idea of the periodic table. And it turns out that that matches very well with what quantum mechanics wants to tell us about it. Okay, so this is the periodic table written in a bit different way. So here we group them, these elements, by their name, and also that refers to their chemical and physical properties. So here we have the so-called alkali metals. So all of them like to lose an electron, as I told you, to become more stable. Here are the alkaline earth metals. They like to lose 2 electrons. So all of these like to form ionic compounds. They are very much able to form ionic compounds when they make some kind of chemical reactions. Then we have a big block of transition metals here. So this is copper, iron, gold, silver, all these things. And also all of them have some kind of similar characteristic, right? They are usually solid. When we look around here, all the metals are usually solid that we see. They have some shine, right? They shine quite nicely, all these metals. So they are conductive often. So all of them have, again, very similar properties. And then we have this green group, which apparently is not like very clear to put it into some name which summarizes their properties. So here we definitely have some differences. We often group them again into 2, like this one here and this one. This has like oxygen, carbon, nitrogen, and here we have a little bit different elements. And then we have the halogens, which, as we know, always like to get an electron to form a noble gas configuration. And then we have the noble gases, which don't do anything because they are happy, right? They have all their electrons. Why should they do any reaction? They're already noble, right? And then we have the lanthanides and actinides, which we will not talk much about. So they are actually inserted into this. You can see they're after barium here. Here we have to insert this row of elements in order to keep the systematic ordering. Okay. So maybe let's look first into metals versus non-metals. So metals have a common property. So this now not only considers transition metals, but also alkali and earth alkali metals. They are all efficient conductors of heat and electricity. They are malleable and ductile, and they have a lustrous shine, right, when you look at them. That's what we usually like also when we see them. And they tend to lose electrons to form positive ions, the alkali metals at least, but also the other metals. Transition metals apparently also like to lose electrons. So all of the metals have this in common. And then there are the non-metals, which are everything else, and they usually lack the physical properties we use to characterize metals. And some of them try to gain electrons in reactions with metals. So usually when you have any reaction of a metal and a non-metal, the metal would usually like to give away the electrons to the non-metal. And non-metals are typically bound to each other by forming covalent bonds, right? While for metals, we know, we already saw that for the alkali and earth alkali metals, they like to form ionic bonds. Yeah? So these are the alkali metals: lithium, sodium, potassium, rubidium, cesium, francium. They are members of this first group, the first column of the periodic table. And they are extremely active elements because they really like to get rid of that electron. So if you have ever seen some experiments putting like sodium into water, you will immediately see a big reaction happening there. Like the sodium will start like basically giving away that electron to water, right? So it will reduce the water to hydrogen gas, and the sodium will basically start flowing and do a lot of gas bubbling happening. So that will happen there. They are very reactive because of their tendency to lose that electron. And then you have the alkaline earth metals, which like to lose 2 electrons. So they form 2+ cations, right? We call this also divalent cations. And then we have the halogens, which I already told you they want to get one electron, usually. Um, and the noble gases, which usually don't react. And then we have the horizontal rows of elements. So we usually call these the periods. So the first row is the first period, second row is the second period, third period, fourth period, and so on. And again, originally, the periods were introduced so that along one of these groups, you have similar elements of similar character, right? Like lithium, sodium, potassium. But later it was found that it also has to do something with the filling of these shells with electrons, as we will look into later. Okay, so which of these forms ions with a +2 charge when they react with nonmetals? Who thinks this is alkali metals? A. B. Alkaline earth metals. Okay. Halogens. Noble gases. And none of these. Okay, so we got it. Should be alkaline earth metals. Now, given these metals, we can start to form compounds, ionic compounds. And we can, for example, start learning a bit about naming of these compounds at this point. And we start with binary compounds. They are composed of 2 elements only. That's why they're called binary. Bi means 2. So they have a cation and an anion. You usually put the cation first and then the anion. And also in terms of the naming, you put the cation first in the name. The cation takes its name from the parent element. And the anion is named by taking the root of the element and adding ide, ite, to the end of the name. So here you have some examples. So for the cations, you can see they are just exactly the same as the element name. This is a magnesium cation, calcium cation, barium cation. And here are the anions. And you can see they are exactly like the element name, but with ide in the end. An oxide anion, sulfide anion, nitride anion, and so on. Okay, by the way, you can see that oxygen is losing 2 electrons, nitrogen is losing 3 electrons, right? So apparently also these elements have some tendency to become noble as well, right? All of the elements tend to become noble, but the tendency decreases a little bit. So you don't necessarily, oxygen doesn't necessarily like completely get 2 full electrons, but they can also start sharing them and they can also become noble with that. So there's a bit a difference to these methods. Okay, name these binary compounds. So the first one is cesium fluoride, aluminium chloride, and lithium hydride. So here you see something interesting. Hydrogen, in this case, is negative. So it has an extra electron. So hydrogen can be a proton, just H+, but it can also become negative. And it can become a hydride anion. Why is this a special thing? Because hydrogen also usually likes to lose its electron. But in some situation, when it is together with a metal, then the metal even has a larger tendency to give away the electron, so that the hydrogen says, okay, then give me the electron, then I become noble with that. So that's also fine, right? So in that situation, you can form hydrides. Otherwise, the hydrogen is most commonly always positively charged in almost all compounds that you can find. Okay. Okay. So now we consider the type 2 of these binary ionic compounds. So this is the nomenclature for the metals which form more than one type of cation. So in this case, the charge of the metal cation is indicated by a Roman numeral. So that usually happens especially for the transition metals, which can have many different charge states. They don't necessarily just lose 1 or 2 or 3 electrons. They can, depending on the partner, have different charge states. Okay, and the common metals that don't require Roman numerals are usually the group 1 elements, because they usually form +1 in group 2. But like silver and aluminium and silver and zinc, so all of these usually have just a single charge state. They don't form different kind of charge state. But for example, copper, chromium, manganese, all of these can be in various different charge states, so that usually we would indicate it with the Roman mineral. And the iron with a higher charge has the ending IC, and the one with the lower charge has the ending OUS. Okay? So based on this, give the systematic name for each of the following compounds. And given the systematic name, write the formula. So we do it in both ways. So let's start with let's start realizing that all of these, of course, contain a metal that can form more than one type of cation. So we need to determine the charge of the cation first, right? So that we can write as a Roman number the charge state. And this we can do by just checking the state of the anion, because the anion is always in a particular charge state. So we can just take that and, like as we did it here, we can just infer the charge of the cation by making everything neutral. Okay? That's the idea here. So example, copper chloride, right? Cl is -1, so copper should be +1, right? Very easy. So we call this then copper 1 chloride. The 1 is here the charge state of the copper. Another example here, mercury oxide. The oxygen is -2, right? We know that the oxygen likes to be -2, then it becomes noble. So it's mercury 2 oxide. Yeah? The mercury has to be +2. Another one, iron oxide. So here oxygen is -2. -2 times 3 is -6, right? So iron has to be 3, because 3 times 2 is then also 6, right? So you have 6 plus -6 is 0, right? So iron has to be 3, well, because oxygen is 2. So we have iron 3 oxide. Okay? Does it make sense to everyone? So this is what you can do if you already know, if you have a metal in there, right? Because metals always like to completely remove their electron, lose their electron. So you can do this simple math. In molecules or covalent bonding, it's not that easy, because the atoms start to share the electrons. So it's not clear where the electrons are. But we come to that a bit later. And now we do the inverse way. We are given this one, manganese 4 oxide. You have to write the equation, right? Then first you write like this, MnO. And then you need to think about, okay, the manganese is 4 plus, so you need 2 oxygen with -2. 2 times -2 is -4, right? So then you have a total charge of 0. Yeah? Lead to chloride. Chloride, again, is -1. You have, and the lead is +2, so you need 2 chloride to cancel out the charge, and you have a neutral compound, PbCl2. Okay, so that's just a little flow chart, how you determine the name. So first you need to think about, is it type 1 or type 2? So do you require to think about the charge state of the cation or not? In the type 1 case, you just use the element name. In the type 2, you have an element which can have different charge states, and you can infer the charge of the cation from the charge of the anion, right? So that's usually how you would do this. Okay, this is just a couple of more examples. I don't think we need to do all of this. You can look into these at home more, like while preparing for the next short test. So this is cobalt 2 bromide. Brom is -1, right? So it's -2. Calcium chloride. Why do we not put the 2 here? Because calcium is always +2, right? Calcium is an earth alkali metal. It's always +2. There's no other state that it would prefer to be in. Chromium 3 chloride, gallium iodide. Okay, so gallium is also one of these elements which always like to be in +3. You can see also, like, if gallium loses 3 elements, it becomes argon, right? Essentially. So always this will, you don't need to indicate, in this case also the oxidation number, or the charge state, sorry. Okay, so these are some of the common cations and anions you find among the periodic tables. So the alkali metals, they're always +1, the earth alkali metals +2, you have the halogens, which are always -1, then you have oxygen and sulfur, which are usually -2, nitrogen, which is -3, aluminium and gallium, which are +3. So for all of these, you don't have to indicate like the charge number for the cations. And then you have these transition metals, and you can see they have different oxidation states. These are not even all of them. Manganese can basically have any charge state until even 7, manganese 7. So it's very complex. So when you go to these transition methods, it's not as simple as thinking something wants to become noble, but you have to really like look into the quantum mechanics of these elements to understand why which oxidation state is stable and why the other one is not. Sorry, sometimes I call this oxidation state because this is actually the right way to say it, but you don't know that yet. So bear with me for a moment, just charge state, okay? Charge state, different charge states of these cations. Okay. What else? So now we discussed about the single atomic ions, right, and compounds. Now also we can have polyatomic ions, as we know. We looked already at this ammonium cation. And they usually are assigned relatively special name that we need to memorize. For example, there are these oxyanions, which are anions containing an atom of a given element and a different number of oxygen. And this is something, there is some logic behind it, but usually also there's some memorizing involved in this. The logic is that the name of the member with the smaller number of oxygen atoms gets usually the ending ite, ite, and the member with the larger number gets the ending ate, ate. Okay. So we will see example in a second. And when there are two oxyanions that make up a series, then you use the prefix hypo, which means less than, for the fewest oxygen. So you have like a hypo, ite, 8, and then you have another per, 8, for the largest oxygen atoms. Okay, so let's see how this works. So for nitrogen can have 2 or 3 oxygen atoms. If it's 2, so we call this nitrite. If it's 3, we call this nitrate. Right? That's relatively simple. We said less oxygen is ite, more is 8. Right? But different elements have different oxygen atoms bound to it. So for example, sulfur has usually 3 or 4, not 2 or 3. So we call the 3 sulfite and 4 we call sulfate. So we cannot say that ite ending has always 2 oxygen. You cannot say that. It depends on the element. Every element has its own like ordering. The ordering stays the same. We start from ite then to 8. Start from ite then to 8. But the numbers are different. Okay. We also have something, sulfur can also get another proton here, and it's called hydrogen sulfate. You see also that the 2 minus has become minus 1 because we add one positive charge, right? This is also called bisulfate usually. We have hydroxide is with a D here in the end. We have cyanide. So these are just common names that we need to just memorize. They have the typical ending of the anion, like chloride, bromide. They have IDA ending. Then we have here phosphate, hydrogen phosphate, and dihydrogen phosphate. So you can add protons to it. You can always reduce the charge from -3, -2, -1. And we add more and more protons to it, right? So that's why we call this hydrogen phosphate, dihydrogen phosphate, and so on. Then we have carbonate. Carbonate is CO3 2 minus. And then we can also add again a proton to this. We can get even one more proton. Then we have dihydrogen carbonate or carbonic acid. And that just decomposes into carbon dioxide, right? That's what you have in all your carbonated drinks. Again, the nomenclature is similar. But again, knowing that this is carbonate, logic is a bit difficult, right? You could also call this carbonite, but it's just called like that, so we need to like bear with it. Probably because for the other elements also 3 to 4 oxygens are usually called 8, so they call this 8. Something we need to just memorize. And then for chlorine, it's actually even more interesting because chlorine can have 1, 2, 3, or 4 oxygen. So we call this hypochlorite, chlorite, chlorate, perchlorate. Okay, so we go in this ordering. And same actually for chromate. We also have like different possibilities there as well. Okay, so these are just some of the examples of that nomenclature of the polyatomic elements. Okay, so given the systematic name for each of these compounds, that's the task, and then the other way around, you have the name and write down the compound. So let's say you have this formula here. Okay, you know it's a sodium, right? Sodium is always +1. You don't need any Roman number. So it's a sodium, and then SO4, that's something you need to know, you need to memorize from the table. This is actually a sulfate anion, right? SO4 2 minus. And that's actually something you can already guess because this is +2, so this should be -2, right? So it's a sulfate, so it's sodium sulfate. Okay, next one, MnOH2. So this is manganese. Manganese can have many different oxidation states, right, as I told you. So we cannot directly say this is +1, +2. We need to look at the anion. And the anion here is OH minus. OH is always -1. It's a hydroxide anion, which is OH minus. So if we have 2 of that, then the manganese has to be +2, right? So that the charge is neutral. So it's a manganese 2 hydroxide. Other way around, we are given the name sodium hydrogen carbonate. Okay. So we put the sodium here, the hydrogen, and then the carbonate. Carbonate is CO3. And then we also only have to think about the charge state. Sodium is +1. And hydrogen carbonate or bicarbonate is -1. Why? Well, CO3 is 2 minus. So if we add a proton to this, then we get HCO3 minus. Right? So it should be -1. So it's already balanced. We don't need any numbers there. Sodium selenate. So again, we have to know the name. Selenate is SeO4, just same as actually sulfate, right? That's very easy because they're in the same group, right? You can see sulfur, selenium, tellurium, So they form, usually, typically they do similar chemistry. So also selenium likes to have 4 around it and form a selenate, like a sulfate. So it's 2 minus, the sodium is +1, so it's balanced. Okay. Okay, now we have another type of elements which is formed between 2 non-metals. Yeah? In that case, the first element in the formula is named first, using the full element name. And then the second element, you put it as it would be an anion, even though it's not an anion. Okay? So if we have non-metals, we said we don't necessarily form ionic bonds. We usually have covalent bonds, right? So in that case, however, in the notation, we still treat them as an anion. And we use some prefix for the naming, for the counting. Okay? So mono prefix means it's 1, di means 2 atoms, 3, tri, tetra, penta, hexa, hepta. These are all the Greek numbers. So based on this, we could do just one example here. So this is phosphorus, right? Phosphorus is a non-metal. And chlorine is also a non-metal. So it's a phosphorus chloride, right? But we have to count how many chlorides there are. So it's a phosphorus pentachloride. So we name this chloride, but we have to remember that this is not a Cl- in this case. Phosphor is non-metal. So the Cl doesn't completely get all the electrons. The phosphor has something to discuss regarding the electrons. It also wants to keep electrons. So they will make some deal and share the electrons, right? Phosphorus trichloride here with 3. So we just use a different Greek symbol. Sulfur dioxide. Okay. And the other way around, you are given the name and you have to put the formula. This is sulfur hexafluoride. So it's SF6. Hexa means 6. Sulfur trioxide, SO3. Right? So for the naming of the binary compounds, we can now extend this. We first determine if there's a metal present. If not, we have to use what we just discussed, the type 3 notation. If there's a metal present, then we have to discuss, does the metal form more than one cation? Right? If no, we can just put the name of the cation and anion as is. If yes, we have to put the Roman numeral to label them. Okay. And then for naming for the polyatomic ion, we have to usually then also consider the name of these polyatomic ions that we discussed. So if it's not just a binary compound with 2 elements, we have to consider this naming convention for the polyatomic ions. Okay, so that's it. Is there any question from everyone? No, of course not. Okay, then let's finish and see you on Thursday.